Hello friends, so today we are going to solve two further questions, and these questions are from rotational motion. And one second. So these questions, both of them, are from the rotational motion, and in the first question it is asked that a uniform stick is held horizontally and released from the rest. At the same instant, one of its ends is given a quick upward blow. The stick rises, rotates, and later returns to its original orientation, that is horizontal, at the same height from which it was released. Determine the possible maximum heights attained by the stick center of mass during this motion. In this case, we are given a horizontal stick and which is given a impulse, okay, and the stick is already at a certain height, okay, but that is not of that much importance. So suppose this is our stick and it is a certain height, and it is given a short impulse, and let us suppose we push it at this extreme end, and length is not given, so let us assume that it is having a length of L and its mass is capital M, and so the length is our capital L and its mass is capital M, and let us suppose this is a center of mass. So obviously this you can say the stick is going to translate as well as rotate, and therefore we can assume that it will be having two types of, and we can solve this question by using two methods. First is our energy conservation, but in case of energy conservation we have to remember that we have to consider the conservation of energy after the impulse has been applied, because impulse is a external force, and because in the presence of external force the conservation principle is not, you can say, valid for that particular. So therefore we are going to consider that just after the impulse, just after impulse, and this is the position impulse we have applied, and like we said, we considered that length is our L and we are having mass is our capital M, and like we said, we have applied impulse J at its one of its end extreme. Therefore we can write that our for impulse J, we can say that linear velocity of the center of mass linear velocity of center of mass, and that linear velocity of center of mass suppose is a v, then this v will be equal to impulse multiplied by m. Okay. So this is our velocity of our center of mass, and from here we can find out the angular velocity. So we can say angular velocity about the center, angular velocity about the center, and let us suppose that is our omega, then this omega will be equal to impulse, and the lever arm, that is our L by 2, and our moment of inertia, that is our I. Okay. So lever arm is nothing but our L by 2 with respect to the center of mass, and the value of moment of inertia, that is I, we already know. Therefore we can write that omega is equal to, this comes as JL divided by 2, and moment of inertia is our 1 by 12 ml square. So here this square goes by the L, and 12 goes by 6. Therefore from here we get that our omega will be equal to 6 times J and our m multiplied by L. So this is our angular velocity. Okay, so it has a tendency to have angular velocity of omega, something like this. And the center of mass, because it is going to have two types of motion, rotational as well as our translational. Okay, therefore we can find out the kinetic energy, rotational as well as kinetic energy, translational. So we can say our kinetic energy translational, that will be equal to over half m v square, and we already know is our J upon m. So this comes as our half m, we have this as a J upon m whole square, and this m and square is going to cancel out, so this will be coming as half J square upon m. And we can calculate our rotational kinetic energy. So we have a kinetic energy rotational, which will be equal to half I omega square. Okay. And we already know this is our half, moment of inertia is our 1 upon 12 ml square, and omega we just calculated is 6 J upon ml whole square, and this will be giving us 6 J square and upon m. Therefore the total energy, or we can say total kinetic energy, let us call this as KE, will be equal to kinetic energy translational plus kinetic energy rotational, and we can say this will be equal to our translation is 1 by 2 Jm square J square m plus 6 J square upon m. So it will be coming as our 13 by 2 J square upon m. And no doubt it's given that the stick is already at the some height, but for the sake of convenience, because this stick will be returning back at the same height, okay, let us suppose it lands somewhere here. Okay, therefore we can assume that their initial potential energy is equal to 0, okay, because the initial potential energy and the final potential energy will be same, so there is no need for it to solve with respect to a potential energy. Okay, so we assume that potential energy is 0 at the initial height. So we can say that our potential energy is taken as 0 at the initial height. So it means the total energy that will be initially will be our entirely the kinetic energy just after the impulse. And now we come to our the maximum height, and the maximum height will be our center of mass. So the center of mass will be traveling something like a projectile. So it will be following this path, something like a projectile, and it will be coming this. Okay, so somewhere here it is going to have a maximum height. Therefore, we can write that, okay, and in case of this projectile motion, we know that our this top of the motion, the center of mass is for a fraction of second is going to have only our rotational energy, a rotational motion, and for fraction of second at the top of this it will be having our the mass momentarily stops in terms of our center of mass. Okay, so we can say that at the maximum height of our center of mass, okay, its velocity, suppose that is our v, which we have taken, is equal to 0. Okay. So it means it's only the rotation continues. Okay. So you can say only rotation continues. And let us call this as our top point as our P. Therefore, we can write that our energy at the top, energy at point P, will be equal to, and suppose this height is our h. Therefore, it will be our potential energy, that is our mgh, plus our rotational kinetic energy. Therefore, we can write this as our mgh plus 6j square upon m. Now we can use our conservation of energy. Conservation of energy after impulse. And we can write that our total energy was our 13 by 2 j square upon m will be equal to our mgh plus 6j square upon m. Now it is quite simple to solve, and from here we can write that our h will be equal to, this is our 12 minus 13 minus 12, so it will be coming as our j square upon 2m square g. So this is the maximum height attained by the center of mass. Okay. And okay, now we come to our, it is said that it should be returning back to our horizontal. position. Therefore, we can say that condition for returning horizontal. And for that, we are going to find out the time of flight for our center of mass. Therefore, we can say that our time for center of mass to return to its original height. Original height, and that is our t. And straightforward we can write that t will be equal to over twice v divided by g, and v already we know, so this comes as 2 by g, and v is our j upon m. And within this time t, we can also find out the angular displacement. So we can say our angular displacement in this time, suppose that is our theta, and theta will be equal to our angular velocity multiplied by the time t. And we simply substitute the values. We know both our omega as well as t. So omega was our 6j upon ml, and t is our 2j upon g multiplied by m. So this gives us that theta is equal to 12j square, and we have this as m square g times l. And it is given in the question that this stick is at the same height, it should be horizontal. Okay. Therefore, we can write that the angular position for our horizontal. So we can say that for the stick, to again appear horizontal, our theta should be the integral multiple of 2 pi, that is 2 pi times our n, where this value of n is equal to 1, 2, 3 and so on. Okay, so this is the important condition, that the stick we start at a horizontal position, it returns to the same height horizontally. Okay. And we just calculated with theta, so we can substitute it. So we can say this as our 12 j square upon m square gl is equal to 2 pi times n. And from here we can find out our j, and our j square will be coming as, this will be given by 6. So we are left with our, this is our pi n, and m square gl, and this comes as divided by 6. So this is our impulse, and we can find out our height, because we know that our height we have already calculated, and that is our j square upon 2 m square g. So this is our j square upon 2 m square g. So we substitute value of j square, this comes as 1 upon m square g times, this is a pi m square gl upon 6 multiplied by n. And here our m square, g and g cancels out, and this will be coming as pi l divided by 12 multiply by our n. Okay. And we can substitute value of n is equal to 1, 2, 3, 4. Therefore, we can say that our value of height will be equal to pi by L by 12. Okay. If we take value of n as 2, so this comes as our pi divided by 6, and we can write this as pi L divided by 4, and so on. So these are the various values of height that can be taken by the stick. Okay. And we solved this by using the conservation, and we can also solve it by using the traditional method of our impulse as well as our constant angular velocity. So let me put it here. So this was our conservation approach. And same question we can approach by using more traditional path. In this case, we can say, let us suppose this is our stick, and impulse is applied to one of the end, and let us suppose length is given as L. So we can say that we have a instantaneous impulse, that is impulse J is applied at one end. Okay. And let us assume that end is over x is equal to over L. Okay. And this is at t is equal to 0. At t is equal to 0. Okay. It means we can write our center of mass velocity. So this is v is a velocity of center of mass. So we can write that our velocity of center of mass, that is over v, is equal to over j upon m. And we also know that this center of mass is going to behave like a projectile. Okay, we discussed in the first part. Therefore, we can say that our center of mass undergoes projectile motion. And therefore we can write that our maximum height, that is our h, will be equal to v square upon 2g, and we substitute the value of v. Therefore we get that our h is equal to 1 upon 2g, and this comes as our j square upon m square. And we can also find out its angular velocity. So we can say that our angular velocity omega will be equal to JL upon moment of inertia. Here L is the length. Okay. And we know that our moment of inertia is our ml square by 12. Therefore we can say this comes as j square, and we have 1 upon 12, and this is our ml square. And so this is JL, not JL square. So the square goes by, and this will be equal to our one second. Okay, so we can write that our this will be coming as 12J divided by ML, and same condition that we can find out that our time, you can say that our time, that's our T, which we just also calculated here, that was our 2V upon G, okay, time of center of mass to return to its original height. So we can say time T, or we can say time for center of mass to return to its original height, that is our T is equal to 2V upon G. And we can simply substitute our value of our velocity, and okay, let it be, we can later on deal with it. And for our value of theta, which we also calculated, so we can say that for the stick to appear horizontal again, for the stick to appear horizontal again, the angular displacement, which is our theta, should be equal to our, which is our omega t, should be equal to our 2 pi times n. Okay. And we can easily substitute our values. We can write this will be equal to our 3J upon ML. Time is our 2V, and we substitute value of V, so this comes as 2J upon mg will be equal to 2n pi. Okay, rest of the calculation are identical. From here we can find out our j square will be equal to our, this will be coming as 2 and 2 cancels out, and value of j square will be equal to pi m square gl, pi m square gl divided by 3 and multiply by our n. And this we are going to substitute in our equation of our height, okay, this equation. Therefore we can say that our height h will be equal to 1 upon twice m square g multiply by, and this is our pi m square gl 3 multiply by n, and this m square g and g cancels out, so this will be coming as our pi l upon 6 multiply by our n. And let me write it separately. So this is our h is equal to pi l upon 6 times n. So we can put various values of n, that is n is equal to 1, 2, 3 and so on, and this will be giving us different values of our height. Okay, so same question we can solve it by using two different approaches. And if required, we can also find out our angular velocity, or we can also find out our linear velocity if they are asked here also. Next question. This is comparatively easy, and it states that at what height should you horizontally strike a pool ball so that it immediately rolls without slipping. So in this case, it is based directly on the formula for our rolling without slipping. So we can say that we have our rolling without slipping, and for this we know our condition that V should be equal to R times omega. So we are going to make use of this basic condition where R is the radius and omega is the angular velocity. V is the velocity of our center of mass. And for that we are going to start, let us apply impulse J at a height h above the center. So it means we have a ball, this is center and its radius is given as small r, and we are applying a impulse at a height h from the center. So this is the point of our impulse. Therefore, and V is the velocity and omega will be its angular velocity. Okay. And therefore from here we can write that the linear momentum which will be our L, and that L will be equal to mass into velocity, okay, and that is our J. Okay. And therefore from here we can write that our V is equal to J upon M, and we can find out the angular momentum about the center. Angular momentum about the center. One second. Okay, so angular momentum about the center. For that we can write the equation that our J h minus R will be equal to I times omega. Okay. And because the pool ball is a solid sphere, so therefore we can write that the moment of inertia, that the value of I will be equal to 2 by 5 mr square. And we can remodify the equation in terms of omega will be equal to J h minus R, and we have this value of I is 2 upon 5 mr square, and which can be written as 5 by 2, and we have this is J h minus R divided by mr square. Now we come to the no slipping condition, and we can just find out the answer. So we can say that our no slip condition, which is V is equal to R omega. Therefore, V is our J upon M, and omega we just calculated is our 5/2 JH minus R, and this is our MR square. And here this R goes by the square, and therefore we can write that our we can also cancel out our J, and we can cancel out our M. Therefore, we can say that our 2mr, can write this as, sorry, not 2mr, but it will be our 2r will be equal to h minus r, and we have this as 5 times. And now it is, this comes as 5 plus 7r is equal to 5 times h, or we can say that our h is equal to 7 upon 5 times r. Okay, so this is our height. Oh, sorry, here I forgot. This height is from the table, not from the center. That's my mistake. So this is the table. Okay, height above the table, not center. Okay, so we found out that our height h from our this table, or we can also find out from the center. So this height is with respect to table, this is with respect to table, and we can also find out with respect to our center. Okay, so you can say that our height with respect to our center will be equal to our, this will be our h minus r, that is (7 by 5). This will be coming as 2 by 5 r. So the height above the center, and this is height with respect to our table. So, and if you make a comparison between the height with respect to our table as well as with respect to the center, we can clearly see that more torque is required than our translational to spin faster to match our velocity v. Then only it is going to, because we have to hold the relation that is our true, which is our rolling without our slipping. And in this case, obviously we can see that our velocity is directly proportional to our angular velocity, r being the constant. So it means higher angular velocity will be only resulting with the help of a higher value of our impulse, that is our value of our h. So this completes all the 2 questions for our today. Okay. Thank you.